Uh, how many of you are familiar with French calculation? Basically, do French calculations routinely, as part of your training, as part of your PhD project, or postdoc project. How many of you? Raise your hand. Okay. Who has never done any French calculation? So, and then we have. Then, if I count, I mean, some of the hands are missing. I mean, so it's either binary stuff. So either you've done French calculation or you've never done French calculation. So again, so who has never done any French calculations? Raise your hand. That's it. And so I assume that the rest has done French calculation. Okay. All right. So so this morning again, it will be an introduction to basically the fundamentals of French calculations, and so this is the synopsis of the lecture this morning. So I will start with sorry.
So you have a
laser pointer is the point in the middle.
oh.
So the synopsis. So I will start with an introduction, basically give you the rationale. Why do we want to do French calculations? And then, arguably enough, you can distinguish the French calculations in two classes. So alchemical transformations, whereby you transmute matter, you transform one chemical species into another chemical species. And the other class is geometrical transformation. So in that case, just moving things around using a number of collective variables that are available to you that are geometric in essence. So let's start with the introduction and why do we want to do free energy calculation? So you may remember the origins of MD simulations, and this guy. So you will see a lot of pictures in this lecture, and I think it's important to know who are the main actors in the field. I mean, what they contributed to the field. So this is Bernie Alder. So Bernie Alder is the one of the pioneers. Can you hear me? Is it better? Much better. Better?
Yeah.
Okay, good. So Bernie Alder, back in the late 50s, with the beginning of the computational era, worked on phase transition in liquids, and he was the first one to apply very simple liquids, to apply brute force MD, so basic application of the Newton's equations of motion. Now, 20 years down the road, came Martin Karplus and Annie McCammon at a time where doing science was very collegial. There was kind of I'm not saying that there is no more collegiality and scientific camaraderie. There is certainly camaraderie here, but you have to journey back in the 70s, and there was this thing in France called the CECAM, Centre Européen de Calcul Atomique et Moléculaire, which still exists. Now it's transposed in Lausanne. But at the time, people would come in Orsay, just outside of Paris, and work for several weeks. I mean, there was some funding. It was a time where people were more generous with science. And it was possible for people from all over the world to come and exchange programs. And this is exactly what happened. So Annie McCammon, Bruce Gellin, and Martin Karplus came to CCAM and worked for several weeks to design an MD code and to apply this MD code to the first biological application, which was running BPTI, so bovine pancreatic trypsin inhibitor, over 8 picoseconds, which led to the seminal kind of pioneering milestone paper in Nature in 1977. That was major. And ever since, there has been a relentless race to go to the largest simulation and the longest simulation. As you can see here, on this scale, I mean, you have scales going in opposing directions. So this is the size scale. So we're trying to reach like larger and larger systems. And in the other direction, of course, we have the time, because the larger system, the smaller the time. And so, as Emma mentioned, I mean, we are now at the stage where we can simulate billion atom system, like essentially an entire protocell. But of course, we cannot simulate that for very long. I think that the simulation was done over like a few nanoseconds using the entire blue waters, which is about 360,000 cores. So those are like the typical architecture where you can run this brute force MD simulations. But what we are really concerned about is what are the relevant degrees of freedom we're trying to play with. I mean, what are the degrees of freedom that are important for the biological phenomena that we're trying to address. So as you can see here, it goes roughly from the picosecond timescale to the second timescale. So with a picosecond timescale, those are like the typical relaxation times that you have in a liquid. So the reorientational correlation times of water, of very simple liquids. The nanosecond to the microsecond timescale would be like the typical time needed for spontaneous binding of a drug to a protein. And in this case, what you see here is a Tamiflu binding the famous H1N1 neuraminidase. And then the microsecond timescale to the millisecond timescale is something typical for folding. So here you have the infamous Villain headpiece, which is a fast folder, folding 6 to 7 microseconds. And then here on the millisecond to the second timescale, now we're addressing important phenomena in biology. This is a transporter that was studied in Emma's group. And this takes place typically on the millisecond timescale. And of course, it's not amenable to brute force MD. So now you have to find tricks. And so this is what free energy calculations are all about. You can see them as tweezers, as computational tweezers, that you can use to anatomize the system and basically select the degrees of freedom on which you want to act selectively, in very selective fashion. So, on the menu of things you can do with free energy calculations, you have kind of repeating or echoing what Emma had already said, but you have like different classes of problems that you can address. So you have recognition and association phenomena. I mentioned Tamiflu binding a protein. This is bar star binding to Barnase, so a protein-protein interaction. You have transport phenomena. This is the glycerol facilitator, which belongs to the family of aquaporins. And what you can see here is a small molecule of glycerol permeating through the channel, and this was studied with free energy methods. And here, finally, you have a conformational transition, which is also something you can study with free energy calculations. In this case, this is a sugar-binding protein, the glucose-galactose protein, which undergoes a conformational transition upon binding of the sugar. So, to address these problems, we have on the menu, we have different routes, different classes of methods. The first class of method is based on histograms. So this is typically umbrella sampling, if you're familiar with this sort of method. So the idea is to basically apply some bias on certain degrees of freedom. So in this case, the dihedral angle, and run your simulation with these biases, and then get a histogram or a probability distribution to find these collective variables at different values in a range that you have defined. And then you can recover the free energy from the bias probability up to a constant. The second class of method that was already introduced by Emad is non-equilibrium methods. And so here the idea is to apply an external bias. So it's usually pulling. So you pull irreversibly along the direction of choice. And then, thanks to Jarzynski, by 1997, you can recover the free energy, but not just from one single experiment. You need to repeat this experiment or this so-called realization. And what Jarzynski demonstrated, so this is like a general formulation on the paper. It should work all the time. In practice, however, you need to do your realization in a quasi-equilibrium condition. And so what this identity, this Jarzynski identity says is that you can relate the free energy or the exponential of free energy to an ensemble of realizations and to the exponential of the work involved in these realizations. The next class of method, which is often used in alchemical transformation, is perturbation theory. This comes from Zwanzig, actually also from Landau, and it relates the free energy or the exponential of the free energy to an ensemble average of the potential energy. So basically, it exploits the malleability of the potential energy and the possibility to transform the potential energy, changing parameters as you want. So transforming one molecular species into another molecular species. This is just like an overview. We're going to go over these methods in detail in a minute. And the last class of method is methods that are based on thermodynamic integration. So in this case, you're not measuring directly the free energy, you're measuring the force acting along a certain reaction pathway. And once you have the force, once you have the gradient of the free energy, then you integrate it to recover the free energy. So this is embodied in this equation. So now, of course, the key question is, we have different methods on the menu. So when should one use one method rather than another one? So let me illustrate this with a problem that we had and we worked on with Klaus Schulten and J.C. Gumbart, who is now a professor at Georgia Tech in Atlanta. So we were interested in protein insertion. Some of you may know that nascent membrane proteins insert in the membrane not just in an unassisted fashion, but they are assisted by a channel, a membrane channel called the Sec translocon. The Sec translocon, which you can see here embedded in a nanodisk, with the ribosome above, that channel and the ribosome kind of plugs itself through its exit tunnel on the translocon, and so it forms kind of a continuous tunnel. And as the chain of amino acid translocates through the exit tunnel, it then goes into the translocon. And then the translocon is able to detect whether the sequence that is being synthesized by the ribosome is a sequence of a membrane protein or a sequence of a hydrosoluble protein. If it's a hydrosoluble protein, then the translocon just stays as is, and the chain just diffuses through the channel to the other side of the endoplasmic reticulum membrane. If it's not a sequence of a hydrosoluble protein, then the lateral gate of the translocon opens, and then the chain of amino acid diffuses in the lipids, where either it starts folding or it meets partner, typically chaperones, which help folding. One of the enigmas was the following, that membrane insertion of arginine, if you do simulations and you try to transfer a single arginine through the bilayer, you'll find that it requires about 14 to 17 kilocalories per mole, which is substantial, but not totally unexpected, because you're trying to translocate a naked charge or nearly naked charge in a essentially hydrophobic environment. But experiment says that it should be much smaller. It should be on the amount of 2 to 3 kcal per mole. So we try to reconcile experiments and simulations. And here's what, when I said simulation, here's the typical setup that was used to obtain the estimate of 14 to 17 kcal per mole. So our colleague who did that, Toby Allen, used the following assay. So he had a lipid bilayer through which was spanning a pseudo-infinite alpha helix, typically polyleucine. And one amino acid was replaced by an arginine. And so he started with the arginine deep in water, okay, and then pulled the helix upwards so that progressively the arginine enters the lipid bilayer, goes up, all the way to the arginine being on the other side. So what you expect is to see a maximum of free energy at z equals 0, that is when the arginine is at the center of the bilayer. And you also expect a symmetrical potential of mean force. This is, I'm using a new word here, so potential of mean force or free energy change along z. So you expect to see for this PMF, this potential of mean force, you expect to see a symmetrical pattern, okay, if you do it properly. Now, if you read the fine print in the SI, in the supplementary information, you'll find out that Toby had to redo the assay multiple times. So it was not like a single simulation where you pull the helix upwards. Because if you do that, even doing it very slowly, you completely mess up your lipid bilayer. Because as the charged amino acid enters the bilayer, it doesn't go, naked. It is followed by a retinue of water molecules that, maintain partial solvation of the amino acid side chain. And as you can see, when you are here at -10, you can see that the membrane is already pretty messed up by the amount of water that is gushing in the lipid bilayer. So what he did, in fact, is that he had to reconstruct for the different position of the amino acid side chain. He had to reconstruct the bilayer around it, right? and run equilibrium simulation doing this umbrella sampling. But But this is the kind of profile that he obtained. And when we thought about this problem and we tried to imagine, I mean, is there a better way to address this question? And we thought maybe it would be more clever, instead of having to reconstruct the assay, to use perturbation theory. But in perturbation theory, so you can imagine you use the same pseudo-infinite helix. But then what you have here, these two red dots, are hybrid amino acids, because we're using dual topology, and I'm going to go to that in a minute. But suffice to say that these two amino acids, these two hybrid amino acids, bear two side chains, a leucine side chain and an arginine side chain. And so imagine that we have here the leucine side chain, and here we have the arginine side chain. And when we extinguish the arginine side chain, then we make the leucine side chain appear, and here we make the leucine side chain disappear and the arginine side chain appear. So basically, at all time, we have a charge of +1. And, and then we can measure effectively the fringe difference, measures effectively the translocation. So we're not interested here, when we do the fringe calculation, we're not interested in the pathway. We're just interested in the difference between what's happening in water and what's happening in the middle of the bilayer. But of course, this vision, or this standpoint, is insufficient to reconcile the so-called compression of the hydrophobic scale. And the reason why in experiment we don't get 14 to 17 kcal, but 2 to 3, we need also to put in the picture the translocon, which is what is used at the biological level. And so we need to do the same kind of simulation invoking the translocon. So we have a pseudo-infinite alpha helix embedded in the translocon, and we do the same transformation. And we make one arginine disappear in water and make it appear concomitantly in the middle of the translocon. If you do that, then you nail down the experimental value. Okay. So as Emad was saying, we have in NAMD we have a whole collection of free energy methods. This is, and I don't want to brag about it, but this is probably the richest code in terms of variety of free energy methods available on the market. So this is kind of the genealogical tree of free energy calculations in NAMD, but it gives you a flavor of what's available, what you can use, the method that you can use. So we have FEP since 2001, and it's still still evolving. Actually, it's currently undergoing a major overhaul. For the better good. We have TI, and this has led to the recent implementation of constant PHMD, which kind of relies on free energy methods. We have this branch with the Weeks Chandler, it's actually WCA, sorry, the Weeks Chandler Anderson potential and Hamiltonian hopping. We have a very important component of NAMD for free energy calculation is CoVAR, so the collective variable module, and that includes metadynamics, Urbana samplings, extended Lagrangian ABF, multiple Walker ABF. We have now scripted variables. I will go to that in a minute. But Giacomo Fiorin, the authors of CoVARs, will give you more detail about this scripted variable. We have ABF, of course, since 2004, GABF, extended ABF, extended generalized ABF. So this is all the methods that you can use. And now let's go to alchemical free energy calculations, which is like the first class of method I want to talk about this morning. So So as I was saying, now we're going to move to alchemical transformations. And so the field of alchemical transformations really started with this guy, whom you may recognize. This is Bill Jorgensen. At the time, he was not too far from here. He was in West Lafayette, Purdue. And he did the first alchemical transformations, so basically using a computer experiment to transform methanol to ethane. That was like one of the pioneering papers, applying a theory that had been there since 1954, but of course never used in the context of chemical transformations. And so this is the paper that he wrote in Journal of Chemical Physics, 1985, and that basically ignited the field. And a few years down the road, then Peter Coleman here, who you may know from Amber, Peter used the same methodology and applied it to problems of biological problems, typically calculating the hydration-free energy of amino acid side chains, analogs, or also doing the first in silico point mutation in a protein. And that gave this two back-to-back science papers. And this is Herman Bergson from Groningen in the Netherlands, the father of the Chromos program, which frequently became Chromax. He was also the father of Chromax. And he applied for energy perturbation to something more physical, chemistry-oriented, basically calculating the free energy change for creating a cavity in a liquid. So the calculations that were done by Bill Jorgensen and by Peter Coleman relied on a paradigm that is called the single topology paradigm, which consists in finding, so you have two states. You want to go from one chemical species into another chemical species. And when you use the single topology paradigm, you have to find a common denominator for these two states, right? So imagine that you want to go from methanol to ethane. You have to think in terms of number of atoms and what is the biggest molecules. It will be ethane. So then you'll have to transform some of the atoms in ethane into atoms of methanol. So typically, you're going from C2H6 or CH3 to CH3OH. So one of the carbons to be transformed into an oxygen, and the hydrogens, of course, remain hydrogens. But in the process, you also have to change the bond lengths. So this is what you do here in the single topology paradigm. So you have to change the bond lengths, make some of the hydrogens appear when you go from methanol to ethane. So this is what single topology paradigm is all about, finding a common denominator. And so how do you transmute one species into another one? Well, you're playing with the potential energy function. So you're basically transforming the non-bounded parameters, so the charge, the van der Waals radius, and the well depth of the van der Waals potential. And you're making them a linear function of some quote-unquote coupling parameter, lambda. And so you just say, well, my charge at lambda going from 0 state A to lambda equals 1 state B, Q of lambda is equal to Q final times lambda plus 1 minus lambda Q initial. Okay, you do that also for the well depths, and you do that also for the van der Waals radius. So it is necessary to correct for the change of the bond lengths, especially if you are shaking the if you are shaking the bond lengths. When I say shaking, you understand what I mean. So I'm applying the shake / rattle constraint algorithm, which is used to eliminate the high vibration that comes from high frequency vibration due to the hydrogens, right? So in some programs you can shake everything. In NAMD we're only shaking bonds that involve hydrogen. Okay? The reason why we do that is to allow. There's a practical reason. The reason we do that is to allow longer time steps to be typically 2 femtosecond as opposed to 1. And it requires electrostatic decoupling. You don't want to find yourself in a position where you have a naked charge, where you have a charge without van der Waals parameters, because that is the recipe for disaster. You're going to have like collisions, clashes of atoms. You always want to have a charge that is protected by a van der Waals radius. So the way we do it is we make the charge disappear, and then we make the van der Waals parameters. So this is a single topology paradigm. There is another paradigm called the dual topology paradigm. This is what we have in NAMD. This is due to the group of Martin Koppers, and can be found in the science paper by Thierry Gao. So the idea here is now you have to define concomitantly the two states. So you have a hybrid kind of residual, hybrid kind of molecule that contains the two topologies at the same time. These two topologies don't see each other, so you have to create an exclusion list. Otherwise, we'll have clashes of atoms, right? We create an exclusion list. The topologies do see their environment, but they don't see each other. Okay. So the way it works is you have these two topologies. As one appears, the other disappears, right? So in this case, the end states are defined explicitly. You have an exclusion list that prevents the two topologies from seeing each other. Now, we're not transforming the parameters, the van der Waals parameters and the electrostatic parameters. We are transforming the actual potential energy function. So the potential energy function at some value of lambda is a linear combination of the potential energy function of state 1, final state, and state 0, initial state. Okay. And it's prone to endpoint catastrophes. So what I mean by endpoint catastrophes is when you make the topology appear, it's very possible that it will appear in a space, in a locus that is already occupied by other atoms, typically the solvent. And to avoid that, we have a tool to do that. It's called soft co-potential. I'm going to go to that in a minute. Branching requires particular care. What do I mean by branching? We have a little bit of a Larsen effect. So what I mean by branching is at which point in the molecule do I want to branch out? Do I want to create my two topologies? This is very important because imagine here that I want to transform methanol into ethane, or let's say threonine into leucine. Oh, sorry, threonine into leucine. So if I try to branch here at this level, at this carbon, that's not going to quite work because you can see that here I'm transforming a CH3 into an OH. My OH here is an electro-attractor group, so it will deplete the charge distribution on the carbon, right? Kind of suck the electrons. So if I look at the charge distribution of these two moieties, I see that the charge on this carbon and on this carbon is very different, right? So branching should be done upstream from this carbon. It should be done at the level of an atom that is really a common denominator between the two topologies, right? Okay, so now I have the tool to transform between topologies. single topology paradigm, dual topology paradigm. How do I get the free energy change? So, if you're touching me as is not going to talk.
Okay. Just try to make it here because it's always on and off.
Is it better? I don't know if it's better. Let's try it. Okay. So to calculate the free energy change, we're going to use free energy perturbation. Free energy perturbation is classically referred to the Svensic form. It's not working well. It's working. Yeah, but it's making noise. So this is the actual perturbation formula which relates the free energy change or the exponential of the free energy change to an ensemble average over the potential energy. And the beauty of this formula, as you can see here, we have this subscript 0, which means that we're doing the ensemble average over the initial state of the transformation. So it requires the sole knowledge of the reference state. So it means that you do a simulation with the reference states. You're generating an ensemble of configurations representative of the reference state. And you're going to perturb at each configuration, you're going to perturb and calculate also the energy representative of the perturbed state, right? And then once you have the delta U, the difference between the initial state and the final state, then you can get, you can calculate your average. So imagine that, let me give you a typical example, very simple perturbation. We are interested in a differential free energy of solvation of an ion. So let's say that we're going from lithium to rubidium. So the only parameter that we need to change here is the van der Waals radius. The charge is constant. So we just generate a trajectory representative of lithium, and at each configuration, we grow the ion to the van der Waals radius of rubidium, and we calculate the free energy. And we calculate the potential energy difference between rubidium and lithium at each state, right? And then, once we reach the end of the simulation, then we just calculate the average. An equivalent of the perturbation formula of Svansic, and I didn't mention that, who is this guy? This guy is Lev Landau. The perturbation formula that is usually attributed to Svansic, 1954, can already be found as early as 1937 in the Landau book of statistical mechanics. This is John Kirkwood. And John Kirkwood, as early as 1935, cooked up this formula, which also provides the free energy change. But as you can see, it's a little bit a different formalism. It's also an ensemble average, but over the gradient of the potential energy with respect to the coupling parameter. Lambda is still, what I was mentioning, a coupling parameter that you use to transform the potential energy from the initial state to the final state. So in this case, we will write here the boundary going from 0 to 1. Okay. So this is all good, but in practice, how do we deal with large perturbations? So for that, one of the key players in the game was John Vallow. John Vallow, whose name is often associated with umbrella sampling, but he also worked on staging. So what I mean by staging is you kind of decompose your pathway into strata, so intermediate states. So there is a reason for that. There is a reason why we want to introduce intermediate states, because if we don't, then we cannot get the free energy. Let me explain to you why we cannot get the free energy. So let's rewrite the free energy or the Svansic formula, but introducing some kind of a Laplace transform. And so we write the free energy change with this integral expression. And the element of integration this time is the potential energy difference. So then we need to introduce, this is very similar to when you write a density of states, right? So you can see PO or P0, this is nothing else than the ensemble average over your Boltzmann factor, right? With respect to the initial state. So P0 of delta U is my histogram. My histogram representing how the different states are sampled according to their potential energy difference, right? So I'm running my free energy calculation, let's say going from lithium to rubidium. I'm calculating my delta U's, and then I'm getting this kind of distribution, right? Now, this is an ideal case. I'm trying to be as simple as possible. I'm making the assumption that I'm in an ideal world where everything is Gaussian. And so in this case, my perturbation theory is second order perturbation theory, right? So my histogram is Gaussian, so here it is. And so a Gaussian multiplied, I look like Donald Trump, sorry. My Gaussian multiplied by an exponential is a Gaussian shifted by beta sigma 0 squared, which is so sigma 0 squared is the variance. It's the variance of the distribution, the Gaussian distribution, the variance of P0. So now you see where I'm coming from. The larger the variance, the more shifted the product of the histogram by the Boltzmann factor will be. Okay? So if my perturbation is large, my variance will be accordingly large, and my distribution will be shifted towards the left, which has a dramatic consequence, because now if I compare P0 and the product of P0 by the Boltzmann weight, then I have all this area here under the curve that ends up in a region that I haven't sampled, right? The consequence of that is that my estimate of the free energy will be erroneous. Be erroneous by that much, okay? So you have to make sure that at all times the perturbation is such that you have an overlap or a full overlap of P0 and P0 times the Boltzmann weight. Okay. So how do you guarantee that? Well, by introducing intermediate states. And so as you can see here, in this case, the ensemble of states for 0 and the ensemble of states for 1 do not overlap. And so I end up with these two curves here. And so, but if I introduce an intermediate state here, then they overlap mutually. So this is the way we do it in NAMD. It's completely transparent for the user, but when you're running a simulation going from 0 to 1 with a certain increment, for all intents and purposes, NAMD is running separate simulations that are pasted together. And so you have like fringe changes for these different simulations. But we're basically summing up the ensemble averages for the different simulations, going from 0 to 0, 1, 0, 1 to 0, 2, and so on and so forth. So let me show you or exemplify the effect of playing with the number of strata, the number of intermediate states. So what I'm comparing here, or what I'm looking at is, I'm doing the simulation forward and backward. What does it mean? It means that I'm going from 0 to 1, but I'm also going from 1 to 0. I will show you in a minute why we need to do that. There is a practical reason. The first practical reason is to see whether there is a hysteresis in the simulation, in the transformation, because I mean we want to respect, or we want to satisfy thermodynamic micro-reversibility, which means that if I do the transformation from 0 to 1, I should get the same result with a minus sign going from 1 to 0. So in this case, I'm transforming, I'm looking at the free energy change of for dehydration of argon. So the assay is very simple. I have a box of water, I have an argon atom, and I'm making the argon atom disappear in the box of water, or I make it appear. Okay. So in black, you have the forward transformation, which is making the argon disappear. And in light, you have making the argon appear. Okay. Now, if you look, I'm using like 4 windows to do the transformation. So basically going 0 to 0, 25, 25 to 50, and so on. As you can see, I have almost no overlap in the histogram going forward and backward. So I can guarantee you that the result will be bad. It's garbage. Now, if I go from 4 windows to 16 windows, you can see that it's a different picture. All the distribution overlap, and overlap more or less nicely. And in this case, the estimate of the free energy will be decent. In the NAMD lingo, when you run your simulation, you invoke a script called FEP.tcl, and then you have this keyword run FEP 0 to 1, 0.0625 n steps. That means you want to go from 0 to 1 with an increment of 0.0625, which is 1 over 16. If you're using 16 windows. And for each window, you're running n steps. We will see that this n steps consist of an equilibration phase followed by a data collection phase over which you calculate your n sample average. The equilibration stage is vital because you want to clean up the slate each time you change the window. You don't want to keep any memory of configurations of the previous state. You want to generate an ensemble of configurations that is truly representative of the Hamiltonian or the potential energy function that you're using at this particular value of lambda, not the previous value of lambda. So another guy that is kind of a big player in the field, although, I mean, he hasn't played for a very long time in the field. He worked at IBM, and he is one of the inventors of quantum teleportation. This is Charles Bennett. But in the field of free energy calculation, he is known for the Bennett acceptance ratio. The Bennett acceptance ratio, kind of interesting that the Bennett acceptance ratio in 1976 was cooked up before 9 years before Bill Jorgensen did the first application of free energy perturbation to chemical systems. So the Bennett acceptance ratio is a maximum likelihood estimator of the free energy change. So basically, it's a variance reductor. It's a much better estimator of the free energy than pure FEP. And it uses, or it combines the statistics accrued in the forward and the backward transformation. So you need to have the 2 transformations. Once you have the 2 transformations going forward and backward, you plug them in this set of self-consistent equations. You don't know what C is, and you don't know what the bar estimate of the free energy is. But what you do is that in the first step, you plug the free energy perturbation estimator, which is kind of your guess at iteration 0. And then you start iterating, okay, until self-consistency. The good news is that the mathematics has been cooked up to also get the statistical error associated to this estimator. All of this is available in a VMD plugin called Parse FEP. And you just need to, once you've done your free energy calculation, your FEP calculation, you just go to Parse FEP, enter your input files or your FEP output files for the forward transformation, for the backward transformation, and let it go. One way to get this forward and backward transformation, which is not quite yet available in NAMD, but will be available in NAMD. Actually, this is something very old. This is something that you can find as early as 1985 in the paper of Bill Jorgensen. This is double wide sampling. At each intermediate state, instead of calculating the free energy change for the forward direction, you calculate concomitantly the free energy change for the forward and the backward transformation. Okay. So, as I was saying, it's crucial. It's crucial to do proper equilibration, to set up a large enough number of equilibration time steps when you do FEP calculations. This is the so-called Hamiltonian lag problem. You don't want your Hamiltonian to lag behind as you move forward, as you move from 0 to 1. You want really to clean up the slate, as I said, and you want to have your configurations to be representative of the actual state you are in. You don't want to keep any memory of the past. Okay. So this is just like an advertisement for the many plugins that you have available in VMD. And so Parse FEP is one of them. Okay, so I mentioned that FEP calculations were prone, especially when you have dual topology paradigm, they're prone to endpoint catastrophe, which means that as you start growing the alternate topology and making the other topology disappear, it's possible that when this new topology, this alternate topology appears, it will clash with atoms that are already occupying the space. To avoid singularities in the van der Waals potential that is due to clashes of atoms, the van der Waals potential has been restated, introducing a scale shift potential, or a scale shift term, in the form of this alpha coefficient. So this is from the school of Andy McCammon. This is the Zacharias, Stratzman, McCammon paper, 1994. Coincidentally, the same year, the group of Wilfried van Gunsteren cooked up an alternate formulation of this soft core potential, but the idea is always the same. You want to shift scale your van der Waals potential. In the NAMD lingo, this is controlled by this keyword, alk van der Waals shift coefficient. In principle, within a reasonable range of values, your free energy change should be independent from your choice of alk van der Waals shift coefficient. Historically, before we had this keyword, we had to do very, very small transformations, close to lambda equals 0 or close to lambda equals 1. Like very incremental changes on the order of 10 to the minus 6, 10 to the minus 7. And then, of course, progressively grow as we are avoiding the clashes. I would say that even with the soft core potential, you still have to be careful when you're growing particles in free energy calculation, especially when you're growing ions, as you can still have possible clashes when lambda tends towards 0 or 1. Okay, so in practice, how do you run the simulations? What do you need to run the simulation? Well, whenever you do a frame energy calculation, an FEP calculation, you need to have an equilibration simulation as a preamble. You need to have a well-equilibrated system. So you need a core file, which contains the coordinates, Cartesian coordinates, a velocity file, and an extended system file, which contains, by the way, who is not familiar with NAMD here? You're all familiar with NAMD, so that's fantastic. So XSC contains the size of the box, okay, of the equilibrated system, especially important when you're running in constant pressure. Now, you also need to run your alchemical transformation, you need an alk file, which is essentially a clone of a PDB file. But in the X, Y, Z, O, you can see B, beta column, you have a flag. A flag of 0 means this atom will be unchanged in alchemical transformation.